Okay, here we go with lesson number 3. This is permutations with restrictions and with repetitions. So we'll start with examples right away. Number 1, in how many ways can all of the letters of the word oranges be arranged if there are no further restrictions? Okay, so we have 1, 2, 3, 4, 5, 6, 7 letters. We don't have anything repeated. So we'll have 7 factorial ways of arranging those letters, and that's going to equal 5,040. B part, what if the first letter must be an N? So if I have to have an N, then I've got one choice. Then I've got 6 spaces left, which means 1, 2, 3, 4, 5, 6 factorial ways I can arrange the rest of those letters, which gives me 720. C part, the vowels must be together in the order O, A, and E. Okay, let's take a look at this. I've got the O, A, and E have to be together. I still have O, R, A, N, G, E, S for letters. So this is going to be like one spot. The R will take up a spot, the N will take up a spot, the G will take up a spot, and the S will take up a spot. So I've got 1, 2, 3, 4, 5 spots. So 5 factorial ways to arrange those spots. And then here, within this one spot, O, A, E, I only have one way to arrange that because they told me that it has to be in that order. So times by the 1 factorial, which is going to be 120. They are going to change that in a second. Okay, what about in how many of the arrangements of the letters of the word brains are the vowels together? Okay, let's start writing. E, R, A, I, they'll take up one spot, N, S. So I've got 1, 2, 3, 4, 5 spots. So 5 factorial ways to arrange those spots. The A and the I have to be together, but they don't have to be in that order. They could be switched around. So that would be 2 factorial arrangements of those two. And now I'll times those together, and I get 240 arrangements. Okay, pause and try these by yourself and then see if you do it the same way that I do. Here we go. Find the number of permutations of the letters in the word kitchen if the letters K, C, and N must be together but not necessarily in that order. So K, I, T, C, H, E, N. I just spell it out like that so I don't forget letters. Okay, then I know I've got 1, 2, 3, 4, 5 spots. So 5 factorial arrangements of the spots, and within this spot I have 3 factorial arrangements, and that will give me 720 arrangements. Okay, what about if the vowels must not be together? Okay, this could be super painful if I did them not being together. What if I do no restrictions, take away what I just figured out, which is them being together? So if I do no restrictions, take away vowels together. No restrictions, I have 1, 2, 3, 4, 5, 6, 7 letters, so 7 factorial arrangements. Take away the 720 that I just found. Oh, wait, I didn't find the vowels together. Okay, the vowels together. K, I, T, C, H-E-N. So I've got 1, 2, 3, 4, 5, 6 spots to arrange and 2 letters to arrange within one spot. So now 5040, take away, this will be 1440, which is going to give me 3600 ways of arranging the letters if the vowels are not together. You can think about this another way, and that is if you kind of think of them as people and you're seating these people on a row of chairs or on the floor maybe. So if I seat the people with no restrictions, so that's going to be the K, T, C, H, and the N. So I've got 5 people to seat. So 1, 2, 3, 4, 5. There they are seated. That's 5 factorial ways that I can do that. And then I need to put the I and the E in between these guys somewhere, and that way they are forced not to be together. There's no way they can. So if I think of this as 1, 2, 3, 4, 5, 6 vacant spots that I could make, 6, and then I want to permute 2 of those ways. And that's going to equal the same thing, 3,600 different ways I can do that. Choose what you like. Maybe try both and see what is your preference. Number 4. Okay, pause, see if you can do this one, and then let's do it together. Here we go. In how many ways can 3 girls and 4 boys be arranged in a row if no 2 people of the same gender can sit together? Let's seat the smallest number first. So if we seat our girls first, we've got girl, girl, girl. So that's going to be 3 factorial ways of arranging the girls. Then I could put a boy here, 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 here. So I've got 4 spots. I'm going to pick and arrange all 4 of those spots. So 3 factorial times 4 permute 4 is going to equal 144 different ways I can arrange those, so none of the same gender sit together. Last one, here we go. 6 actors and 8 actresses are available for a play with 4 male roles and 3 female roles. How many different cast lists are possible? Okay, this one you have to think about, why is it important that we care about the order? Because later on we're going to do where order doesn't matter. So what you're thinking is, if I have 6 actors, so 6 males, and they fit into 4 male roles, so I only need to cast 4 people, doesn't matter who I choose. Doesn't matter for these 4 roles if I'm doing Gaston and LeFou and the Beast and whoever for my 4 main roles. Does it matter which actors, or should I just pick 4 actors and then put them in there and who cares? One night they can play one role, one night they can play the next. Definitely no, they cannot. It matters if Ricky is LeFou or if Ricky is Gaston. Those would be totally different things. So order matters on this, which means I'm going to be able to use permute. So 6 actors, and I need 4 male roles. So I've got 6 males, and I'm going to pick and arrange 4 of them. And I need 3 females, and I have 8 that audition. So I've got 8 females, and I'm going to pick and arrange 3, one of those being a position for the rows, equals, times those guys together, and I get 120,960 different ways that I could cast that play. Okay, and we're just going to think about this for 1 second. That is only with 6 actors and 8 actresses. That's only 14 people that audition, and that's only casting 7 of the roles. You get that many choices. Think about the craziness it is to cast a play that has 24 people in it. So many, many different options available there. Okay, next page. We get to skip. Nice. Okay, this guy. This is, what about if there are letters that repeat? Because so far, all of our words that we've arranged haven't had any repeating letters. So the rule is always, you're going to do however many letters total you have, factorial, divided by any of them that repeat, how many times, factorial. And you'll see what I mean with the bottom. So find the number of permutations of the letters in the words Vancouver. So if I think, and I write this one out and put my repeating letters together, so V-A-N-C-O-U, there's another V-E-R, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 9 factorial letters divided by the repeaters. The V repeats twice, so 2 factorial. Gives me 181440. Okay, mathematical, give it a try. And here we go. M-A-T-H-E-M-A-T-I-C-A-L, mathematical. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 factorial divided by, I've got M that repeats twice, so 2 factorial, A 2 factorial, and the T 2 factorial. All of those in the denominator. And remember, if you're doing this on your calculator, you've got to put brackets around that whole thing on the bottom. And I would think 2 factorial, oh yeah, that's just 2. So don't bother finding all the buttons for factorial. You can just do divided by 2 times 2 times 2 in brackets on the bottom. And we end up getting 1995840. And I hope that you got that one. Okay, then we're going to think of stories that end up in the same thought process as if it were letters in a word. So here's Brett, and he's going to the store, and he buys a carton containing 10 mini boxes of cereal for Christmas morning. There are 3 little boxes of Corn Flakes, 2 boxes of Rice Krispies, 1 box of Cocoa Pops, 1 box of Shreddies, and the remainder are Raisin Bran. Over a 10-day period, Brett plans to eat the contents of 1 box of cereal each morning. How many different orders are possible if on the first morning he has Raisin Bran? Okay, so let's think of this as a word. We've got 3 boxes containing cornflakes. So we've got cornflakes, cornflakes, cornflakes. Then 2 boxes of Rice Krispies, R and R. Cocoa Pops, I'm going to put as a P. Shreddies, only 1 S. And then Raisin Bran, I'm going to use B for bran, and that's the rest of them. 1, 2, 3, 4, 5, 6, 7. So I've got to have 3 of the bran. And now that's just my word. And so I'll use those letters, and we'll see how many orders are possible. How many different orders are possible if on the first morning he has Raisin Bran? Well, if the first morning he's got bran, I've only got one way of him doing that. That's forced. So goodbye to that. We're just going to assume that that happens, And now we're going to go on with the rest of the story as if they didn't even tell us that, because it's forced to happen. Here we go. So I've got now 9 factorial letters, kind of, and let's divide by the repeaters. So 3 factorial for the C's, 2 factorial for the R's, and 2 factorial for the B's. Gives me 1, 5, 1, 2, 0 ways of him eating those cereal choices. I know, it doesn't seem like that would be possible, but lucky him. What an option he has. Okay, next one. Paul and Catherine are considering the following problem. Find the number of roots from A to B if the roots must always move closer to A. Okay, this is you at school. And this is how many roots for you to get to, I don't know, where do we want to go? Oh, B, the bargain barn. And this is saying you always have to move closer, because obviously if you went here, down, and then you could backtrack, there would be an infinite number of ways. So we're always moving closer to the bargain barn. Let's look at this on a worksheet that is similar. So if I'm thinking of going from A to B and now I just have a smaller box, I could go here. I could go all the way over and down. That would be one way. I could go right, down, right, down. That would be a different way. I could go down, right, that would be a third way. I could go all the way down and then all the way over, that would be a fourth way. Is there anything else I could do? And as you can see, super painful to look at listing out all of those possibilities. If I started on this next one, worse, and if I get all the way down here to the bottom where these overlap, that would be not something I would like to do. So there's a nice little way we can do this, and I call it counting corners. I don't know if it really has a name, but that's what I refer to it as. So you're going to start at A, and then you're going to think, this is you on your little bicycle. You've got one way to get to this intersection. If you keep riding, you've not turned anywhere, you haven't changed directions at all, you still have only had one path getting to this end corner. So same thing vertically, 1, 1. Then this intersection, you're thinking, well, I could ride my bike here, and I could ride my bike coming from there. If I add those two together, that would be 2 ways of getting to that intersection. And then you just keep adding those corners together. So diagonal corners add together, and I'm thinking 2 ways coming from the north, 1 way coming from here. So I've got 3 ways. This, I've got 3 ways, and then 3 plus 3 is going to give me 6 ways total to get to B. And here I only found 4 of them. So somewhere my other 2 are there, and you can probably see what those are, but obviously I didn't find them when I did them the first time. So 6 ways total that I can get to B. Let's do it on this one. So draw that out, give it a try, and now let's do it together. So I've got 1 way, 1 way, 1 way, all the way across, and then same all the way down. And now this intersection, I'm just going to add the lines that come into it, or add those roots together. So I've got 2, then 2 plus 1 is going to give me 3 here, 3 plus 1 is going to give me 4, next row, 1 plus 2 gives me 3, 3 plus 3 is 6, and 6 plus 4 is 10. Okay, draw number 3, give it a try, and we'll see if we get the same answer. And here we go. So 1, 1, 1, 1, add those together, and we get 2, 3, 3, 6. And now here, this 6 just continues across because this is the only thing coming into that intersection. So I've got 6 plus nothing else. And keep going all the way across, just like you did with the 1s, and all the way down. 6 and 6. So now 6 plus 6 is going to give me 12. 12 plus 6 is 18. 18 plus 6 is 24. And 6 plus 12 is going to give me 18 here. 18 plus 18 is 36. 36 plus 24 is going to give me 60. 60 roots if I have that scenario. So this would be having to go through whatever point. Okay, draw number 4 where they overlap. And do it. And pause. And now let's see. Okay, so 1, 1, 1, 1. 1 and 1 is 2. 2 and 1 is 3. Next row, 2 and 1 is 3. 6 here. And then this 3 continues. So 3, 3. Going down, this 3 continues if there's nothing else to add with it. And now I'm going to add my corners. So 9 for here. And I'm going to come back up here. So I'll have 9 for there. 9 and 3 is 12. 9 and 9 is 18. And 18 plus 12 gives me 30 ways to get to B. I could go backwards. It would be identical. I could go, they could move it and have me go left to right. Doesn't matter. Okay, there's an interesting way that on here they also have you approach this. So if we do the school going to the bargain barn, this is the same as we did with the second example on the worksheet. And we ended up with us having 10 possibilities. So it's this guy. And what they're saying here is you can also think of this as a word. So if I go here one way, that's like going right. So 1R, and then I'm going right again. So right, 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 and then down, down. That's one way to get to B, but if I arrange those in all the possible arrangements, that would be every route. So it would be right and then right, right, down, or down, right, right, right. So really I have a word that has 3 R's and 2 D's, so 5 letters total, divided by the repeaters, so 3 factorial and 2 factorial. And that will also give me 10. That's really nice for situations where you just have a block, but here you would have to do both blocks separately, times them together. And then here, there's no way to do that one using the write, write down method. So I think when you have small, well, they're only going to give you small pathways. I would just do counting corners. It'll work every single time. Great big huge if you have a box, then yes, the write, write down idea is a good idea. Okay, let's see if we have anything else. No, that is the end. You get to do questions now. Okay, have a good time. We'll see you tomorrow.